Okay, guys. Now we are about to begin looking at the concept of lines, lines in space. We know when we were in the plane, when we were looking at 2D, the equation of a line was just given by the simple equation yx is equals to y is equals to mx plus c. Okay, so let's what about, let's see what happens if we have a line in space in the xy z instead of just in the xy plane. But what if we are in the xyz space? Then what happens? What form of equation do we have for a straight line? So suppose we have a line. Let's say we have a line L in space, which is passing through the points P naught. So this line, as okay, so we have a line there, as you can see on the diagram. So we have a line L, and this line L, we just pick any point on the line. We just need one particular point. So remember, even as when we're looking at lines in remember when we're looking at lines in 2 dimensions, so we had some form like this, x minus x naught. So for us to be able to describe this line, we needed to know at least one particular point through which the line is passing through. So even here in 3-dimensional space, we also require that we know at least one point through which it's passing. So it can be anywhere. So let's say it's here. So it's at the coordinates x naught, y naught, z naught. Then the other thing we needed to know was the slope. So let's see if we need to know the slope of a line in space. Okay, so let's see if we need to know that. So the other thing, parallel to a vector. So remember, in the plane we were looking at the slope, right? Of course, if two lines have got the same slope, which means they're what? They're parallel, right? So now it's kind of difficult to kind of measure slope, because now we're in space. Because slope, we're measuring it as a change in w, change in y over change in x. But now if we include the z, it's kind of difficult to do that. So the easiest way to do that is to introduce the concept of vectors. So the concept of a vector. So if the line is parallel to some vector, so if we're able to construct a vector that's parallel to that particular line, then we can describe the line, because the vector then has everything to do with the that slope. So that's basically. So now if we have a vector which is parallel, so let's call this vector v. Normally it's called a directional vector because it gives direction to the line. So the line is a set of all points x, y, z, for which the vector, if I construct a vector to some other point which is x, y, z, at any point x, y, z, of course all these particular points are on the line. So any point p at x, y, z, such that the vector p naught p1 is parallel to what? Is parallel to the vector v. And actually, this vector v is not the only vector. If I just multiply this vector by some quantity, whether to either reduce it or to either make it point the opposite direction or to either enlarge it, it will still be parallel to the line. So meaning there are so many such vectors, so I can multiply this by some quantity t, subscalar t. So which means actually that the vector p naught p should be parallel to all vectors t multiplied by the vector v. So the value t takes values between negative infinity to positive infinity. So it can either be negative or positive. Okay. So then what are we saying if we say p naught p, that vector there is equals to t times v? So all we are saying is, how do we get p naught p? P naught p is just we subtract the coordinates from here and there. So we have x minus x naught, y minus y naught, z minus z naught. Then we multiply them by the standard unit vectors, and then we get a linear combination. And then this is equals to t. Then we multiply by v there like that. But then remember, the line is a set of all point x, y, z. So which means I'm interested in x, y, z. So then I can expand this, and then take the x naught, y naught, z naught the other side, and of course they are negative this side, so they will be positive the other side, and they will. So x naught I, y naught I, z naught k plus some vector there, and then this will give me all the vectors. So this vector is a positive vector. P is a positive vector, or maybe let's call it r. So we can call it, and as you can see, it depends on the value of t. So we can call it r of t. So r of t takes it. R of t is from here to any point. So meaning all these points will be the set of all points, which means they describe that line. So which means actually in space, for us to be able to describe a line, we don't actually need an equation like this one. What we need is a vector equation like this one here. So this is a vector equation, just to make it more clear. So so what thing do you need for you to be able to describe a line, a line okay, what do you need for you to describe a line in space? It's a vector equation. So what do you need for you to construct that vector equation? You need two things. You need to know, first of all, one, the point through, just one particular point through which it is passing, and a vector v through which it is parallel. Then you can just say that then the vector equation is r of t is equals to r naught. So r naught is just basically r naught is the position vector to the point p naught, right? To the point p naught. So it's x naught I plus y naught j plus z naught k, such that our point P is x naught, y naught, z naught, and then we have some vector v, so we can multiply that, then we have our vector equation. So this is what represents a line in space. So where r is a position vector of a point, that one, and on the line, and r naught is a position vector for that particular point that you know. So that's how we get the equation in space. But then maybe that is a little bit more elaborate. Maybe so. The other way to represent it is to use parametric equation. So we can the vector equation, we can parameterize it. So how do we parameterize it? So what we want is we can begin to look at x alone. So we only look at x alone there and there. So we can actually say that x is equal to the x naught there plus the t v1. Then also the y alone. So y naught plus t v2. Then we also look at the z alone. So z is equals to, it's like looking at a component now. So that's what we're doing in terms of parameterizing. Z naught plus t v3. So that's what. So these three are called parametric equations. So if you represent a line by either a vector equation or these parametric equations, then you have represented it. So we also have another form here, which is the parametric equation of a line. So if you have a vector which is passing through that point and parallel to the vector, then these are your parametric equations. And of course, don't forget that t takes in any value between minus infinity and plus infinity. Okay, let's take an example. So let's find the parametric equations of a line through that point and parallel to the vector, that one. But of course, we know that the first thing is get a vector equation. That's when we can get the parametric equation. So how do we get the vector equation? Remember, the vector equation is r of t. Let's not forget, r of t is equals to r naught. This is the equation that you always need to remember, times vt, right? Perfect. So now what is r of t? So r of t is equals to, what is r naught? R naught is a position vector for that particular guy. So we can even use the component form, minus 2, 0, 4, plus our v here in component form is 2, 4 minus what? Minus 2. Okay, we use angle bracket, then multiply by t. So this is the vector equation. Of course, if you want, you can put it in terms of either the ijk's. You can put it I, but remember this is this minus 0, so we'll still have that. So that's your vector equation. Then in parametric form, it means then I want x in form of the x component, so minus 2. The 2 there multiplied by the t, so plus 2 t. Then the y will be 0 plus 4 there times t, 4t, so it's just the 4t. Then for the z, we have 4 plus times negative, there's minus, so minus 2t. So these are the parametric equations for a line, and they will describe what they'll describe a line for us. Okay, perfect. Another interesting question, maybe a last example. So find the parametric equations for the line P passing through that point and Q passing through it. So it's passing through 2 points. So we can choose any of these points to be our point through which it is passing, but then we don't have one thing. We don't have a vector which is parallel to this. But then since we have got 2 points, we can create such a vector v. We can create the vector v by taking maybe PQ, for example. So remember, now we're just subtracting. We subtract the Q from the p's, right? The p's from the q's, because I'm going from p to q. So it will be now 1 minus 3, so 1 plus 3, that will give us 4, minus 1 minus 2, that will give us minus 3, then 4 minus 3, so that will give us 7. So that's our vector v, and then we can pick p to be one of our points, so which means we have r0 is the, will just be given by what? Minus 3, comma 2, comma minus 3, so that our vector equation r is equals to r naught, remember r naught, plus t v. So our r in terms of vector, it will be minus 3, 2, minus 3. I would have used the, if you want I can use it in terms of unit vectors, there's no problem, or I can use it in this particular form, t times our v. Our v, we formed it there, is 4 minus 3, 7. Then we can get the parametric equations now by just getting the components. So the x part, x is equals to minus 3 plus what? Plus 4t, as you can see there, just get that, and that. Then y will be 2 plus, but of course there's a minus there, so minus 3t. Then the z will be minus 3 there, plus t times 7, so plus 7t. So this is what we have in terms of a parametric equation. So this is exactly how we describe a line in space. So the only thing you need to remember all the time is that for you to describe an equation in space, equation of a line in space, you need two things: a point through which is passing, which will help you form this position vector, and you also need a line, a vector parallel to that particular line. Then you can have your vector equation, and then you can get your parametric equations. All right, thank you very much. See you next time.